All right, in this section, we're going to be talking about the addition rule. Now, to begin, we're going to define what it means to be mutually exclusive. Okay, so to define mutually exclusive, it says the two events, A and B, are mutually exclusive when A and B cannot happen at the same time. Okay, so I'm going to create a Venn diagram here to kind of represent what that means. So here we have every event that can possibly happen, okay? And we have two events, A, and we have an event B. If they're mutually exclusive, that means that they do not intersect. So notice that here we do not intersect those two events. So they cannot happen at the same time. So this would be mutually exclusive, okay? Now, if they were not mutually exclusive, then the picture would look similar to this. So I have two events, A and B. However, this time they have this intersection. And remember that this intersection is the part where both A and B are happening at the same time. So an example of this would be you draw a card from a deck of cards, and you're looking for the probability that it's both a 2 and a heart, right? Where mutually exclusive would be looking for something, maybe it's a 2 and a king. Okay, so this event can't happen at the same time where you can have a 2 of hearts. Okay, so taking a look at some examples, it says we want to determine whether the events are mutually exclusive, and then we're going to explain our reasoning. Okay, so it says the event that we roll a 3 on a die, and then event B is the event that we roll a 4 on a die. Okay, so can we roll both a 3 and a 4 at the same time? Well, no. So this would be mutually exclusive. Okay. Now, looking at number 2, it says the event A is selecting a male student, and event B is selecting a nursing student. So because we know that you can have both a male and a nursing student at the same time, this would be not mutually exclusive. Okay. And then number 3, it says we randomly select a blood donor with type O blood, and then randomly select a female donor. Okay, so females obviously can have type O blood, so this would not be mutually exclusive. Okay, because again, we can have females with O-type blood. Okay, so looking at the addition rule, it says that the probability that events A and B will occur, A or B, so that key word there is the or, and we denote it using the probability of A or B, is given by this equation here. Now, this is the one that you want to memorize. Okay, now if they're mutually exclusive, then this end part actually equals 0, okay? And so we can simplify it. So if we have that they are mutually exclusive, okay, so events A and B are mutually exclusive, we can simplify it to this, where we get rid of that minus A and B portion of it. Okay, so again, that's just a simplified version. The green highlighted part is the one that you actually want to memorize. All right, so let's do an example of this. It says you select a card from a standard deck of 52 playing cards. We want to find the probability that the card is a 4 or an ace. So the first thing we're going to take a look at is whether or not this is mutually exclusive. Okay, so we're looking at a 4 or an ace. Well, can we have a 4 and an ace at the same time? No, we cannot. So these are mutually exclusive. Okay, so when we write this, what I'm going to do is I'm going to say, well, we want the probability of a 4 or an ace. Okay, so the probability that we draw a 4 out of a deck, well, we have 4 4s in a deck out of 52. Okay, plus the probability that we draw an ace out of the deck, well, that's 4 aces out of a 52 card deck, minus the probability that they happen at the same time. So we just said that this is mutually exclusive, so we have 0 that are both aces and 4s. Okay, so what we get here is 1 out of 13 plus 1 out of 13 Okay, and notice that 0 out of 52, well, that just goes away, it's 0. So we have 2 out of 13. That's our probability. Now we do need to change this to a decimal, so we get approximately, I'm just going to round to the thousandths place here, we get approximately 0.154, or about 15.4%. Okay, so this is what we're looking for, is the probability that those events happen. Okay, so looking at part 2, it says you roll a die. We want to find the probability of rolling a number less than 3 or an odd number. Okay, so we're looking at a probability of less than 3. So we'll say less than 3 or odd. Okay, well, what's the probability of rolling a number less than 3? Well, we have 1 or 2. Okay, so there's 2 possibilities out of 6, plus, well, the number of odd numbers in our on our die, well, there's 3 out of 6. We're going to subtract the ones that are potential duplicates. So we have minus something over 6. Now, to do this, what I could do is I could list out the numbers, right? So we have 1, 2, 3, 4, 5, and 6. Okay, then we're looking at the numbers less than 3. That's just 1 and 2. Okay, and then we're going to look at the numbers that are odd, which is just 1. So we have 1 that is both odd and less than 3. Okay, so we're going to do this. So this gives us equals, everything's got the same denominator, so we can put it all over 6. This would be 2 plus 3 minus 1. Okay, so that gives us, let's see, 2 plus 3 is 5, minus 1 is 4 out of 6, or approximately 0.667. Okay, so that's again what we're looking for here. Okay. Now, number 3, it says the frequency distribution shows the volume of sales in dollars and the number of months in which the sales representatives reach each sales level in the past 3 years. We want to use the sales pattern to find the probability that the sales representatives will sell between $75 and $124,999 in the next month. Okay, so to do this, what I'm going to do first is take the frequency. Now, this is 3 years, so we know that the frequency, or N, is 36. That's the total number of possibilities. Okay, now we're looking for the probability that we get between 75,000 and 124,999. Okay, so 75,000 to 124,999. Okay. Now, we have 2 events here, right? So we're looking at from 75,000 to 124,999. Well, we know that this is mutually exclusive, right? The events are separate. Okay, they can't happen at the same time. Okay, so we have 7 out of 36. Okay, that's the probability that it lands within this range, plus 9 out of 36. Okay, that's the probability that it'll land within that range. Okay, minus, well, they don't happen at the same time, so minus 0 divided by 36. Okay, simplify this, well, we get 16 out of 36, which approximately is 0.444, or 44.4%. Okay, so this is our probability that it'll happen. Okay, so moving on, example 4, number 1, it says a blood bank catalogs the types of blood, including whether it's Rh positive or Rh negative, given by donors in the last 5 years. The number of donors who gave each blood type is shown in the table. We want to find the probability, in number 1, we want to find the probability that we select at random a type O blood or a type A blood. Okay, so again, the first thing we want to look at is, are these mutually exclusive? So can you be both type A and type O? Notice that they are 2 separate columns, so these are mutually exclusive. Okay, so we have the probability of type O or type A is equal to, Okay, we know that the total number of patients that we saw was 409, so that's what our total is going to be out of. So we have 409 plus 409, and since this is mutually exclusive, we don't need to worry about that last part. Okay, so the probability that they have type O blood, well, type O blood is this column here. The total number is 184. Okay, and then the type A blood has 164. Okay, we're going to add these together, and we get approximately 0.851, or about 85.1% chance that the next person that walks in to give blood will have either A or O blood. Okay? Let's look at part 2. It says we want to find the probability that the donor selected at random has type B blood or is Rh negative. Now we need to look and see whether these are mutually exclusive or not. Okay, so do we have in our type B blood, do we have anything that is Rh negative? Well, yeah, we do. We have it right there. Okay, so these are not mutually exclusive, so we do need that probability of both B and Rh negative section. So we're going to say we've got the probability of B or Rh negative. Okay, so the probability of B, we have that this is out of 409 patients, right? So we have a total of 45 out of 409 who are B blood, who have B type blood. Okay, then we're going to add the total number of people who are Rh negative. Well, the total number of Rh negatives are 65 out of 409. Okay, minus the intersection. So this is our intersection here. So we have a total of 8 out of 409 patients who are both B and Rh negative. All right, so we're going to simplify this. Again, I'm just leaving this to your calculator. You have that this is approximately 0.249, or just about 25% are B or Rh negative. Okay. All right, so the last one. In the figure to the right, we want to find the probability of randomly selecting a draft pick that is not a linebacker or quarterback. So what I want to do here is I want to actually find the complement. So we want to find, first of all, what the probability of actually finding a linebacker or quarterback. Okay. So we're actually going to find the probability here. So to find the probability of finding or picking a linebacker or quarterback, well, we have how many total people inside of our in our draft. So there are a total of 253 players picked in the draft in 2016. So we have 253 on the bottom, right? And then we need to know how many of those are quarterbacks. Well, in this case, the number of quarterbacks right here are 15. Okay, plus what's the probability of picking a linebacker? The linebacker is dead down here, so that would be 34 out of 253. And notice that these are mutually exclusive. You don't have any quarterbacks who are also linebackers. So we're simply going to combine these. So we have, let's see, that'd be 15 plus 34 would give us 49 out of 253, which is approximately 0.194, okay, or 19.4%. Now, what we're actually looking for is the probability that they're not a linebacker or quarterback. So the way we can do this is say, well, we're looking at the probability of not linebacker or quarterback is equal to 100% minus the probability that they are. So we're looking at, this is the complement of what we just found. Okay, so when we do that, we get that this is equal to 0.806. Okay, so we have an 80.6%